turbulent is chaotic flow. But we really want to dig into boundary layer. And I want to go another layer of depth here this morning with it. So we looked at this diagram before, and the questions you're wondering is why you have dimples on the golf ball, and why do you have the shark skin suit, and why did Mythbusters dimple the car in one of their episodes, which I think I had the link for. I can't remember right now, but I'll get that for you otherwise. And what you're looking at, both of these views here are cross sections of flow and pipe. And one of the terms here we need to know is a Reynolds number. So Reynolds number is the inertia over the viscosity. So inertia is mass times velocity, basically. And then viscosity is resistance to flow. So oil has high viscosity, water has medium viscosity, air has low viscosity. And then the inertia term on the top, the numerator, is velocity. So it's velocity, basically, over viscosity. And what that's saying is if air is going at a certain speed, it might have a Reynolds number of, say, 4,000. If oil is going at the same speed, it will have a Reynolds number of, say, 500. Okay, same speed, but because the viscosity of the oil is heavier, the Reynolds number is lower. And the reason we care about Reynolds number is because that tells you whether you have laminar or turbulent flow, which affects drag and it affects heat transfer that we'll explore here. And you can see right here, that's where the 2000 comes from. So there's a range between turbulent and laminar flow. And I want to show you some little more elaborate drawings and just kind of talk about a couple things. So I hope you find this interesting, but I don't want it to be overwhelming because what we're really interested in is practical applications here, but I think this would be helpful. So you have these two boundary layers that arise, and what happens if you look at the simplest, well, let me say the bottom line concern for us is whether you have laminar or turbulent boundary layer. And the reason for that is laminar or turbulent boundary layers will generally give you better heat transfer and lower pressure drag. They're generally better. But the problem is they come at higher velocity. And higher velocity is bad for friction drag, and higher velocity generally costs money. Right? It uses more energy to move things at a higher velocity. So this part I'm going to go into with a little more depth than I did last time, which I hope will be helpful. So what we're looking at here is flow over a flat plate, which is often how you kind of start these things. So the piece on the bottom is a flat plate. And when you have this airflow going over the flat plate, and it always starts out laminar. Well, almost always, unless it's artificially tripped with roughness or something like that. But let's say it's a reasonably smooth plate. It starts out laminar, even at a high Reynolds number. So in this case, we'll say this has a Reynolds number of 4,000, which means it's high enough to turn into turbulent flow. If the Reynolds number was lower, the velocity was lower, say 1,000, it would never be turbulent. Well, yeah, it would never be turbulent flow. So what happens is laminar flow, then you develop laminar flow initially, then you get this transition section, which the Moody diagram sort of illustrates as well, where you get a mixed type of flow, and then you get turbulent flow. And what I wanted to do was go into this other level of depth, talking about especially the laminar sublayer down here, the viscous sublayer, and the boundary layer of the turbulent flow itself. And this isn't the diagram I'd like you to recall. I've got another one that when you lock things in your mind, I think you'll find more helpful. So here's the thing to note, but this is sort of academic, I think. The turbulent boundary layer is actually thicker. It's actually thicker. But the low velocity part of the boundary layer is thinner. Okay, so if you calculate, like laminar boundary layer, you can calculate really well. Turbulent boundary layer is tougher. It uses numerical methods of estimation. But what I'm saying here, and I guess this graphic hopefully helps, you have a viscous sublayer and this buffer layer. So you have a layer, as the flow is going across the flat plate. The air molecules, nitrogen and oxygen primarily, are sticking to each other. Well, they're also sticking to the plate. And the velocity at the plate you can consider to be zero. So if you look at this velocity profile here in the green, this is a velocity in the boundary layer, which is basically the same above the boundary layer too. And you see these vectors that get smaller and smaller and smaller until you get to zero. So what's basically saying is the molecules, the air molecule that's touching the plate is sticking to the plate. It's hitting all these disparities, these little nooks and crannies, and stopping. And then it is holding by the hand, we'll say, the molecule next to it due to these surface forces, and it's slowing down that molecule, which in turn is slowing down the other molecule. So these molecules here, these molecules at the base, let's see if I can write this. These molecules here are going at no velocity. These molecules here are going at a higher velocity. But they're being held back by the slow-moving molecule that's wanting to stick to the base. So you remember when we looked at phase changes, this surface forces, the stickiness is real important for that as well, determining phases. So just to remind you again, the notion of molecules being ball bearings or anything like that, you need to completely throw out of your mental imagery, because they're not. They're much more like kids having fun at a playground holding hands. Or they're sticky. They want to generally be with each other, and that's what's occurring here. And what's really interesting with this is you get these kind of different types of regions. So when the real low velocity stuff in this viscous sublayer, the laminar layer, the molecules that are really close to the surface, well, they're going slow. And if something's going slow, it has a low Reynolds number. It does. And if it has a low Reynolds number, it's laminar. It does. And that's what you get there. You get this really thin laminar sublayer. And then it gets bigger and bigger as it goes on. So what I think, I'm trying to think, well, let me just, one other little last detail here, just going kind of far afield, and we'll take a break here and just, whoops, just a bit, is, oh gracious, is what's happening is when you talk about fluids, you talk about shear stresses, just like we did with solids. So you have shear stresses. And the shear stress on this flat plate can be calculated. And if you take that shear stress and multiply it by the area over which it acts, that's equal to drag. That's equal to force. So shear stress times area equals force, drag force. And the way you calculate that then is you take differential elements, those tiny differential elements we talked about, integrate over the area that you're flowing over. So, and the reason I mention this is in fluid dynamics, as you move into that terminology more, you'll hear terms like shear rate, shear stress, whereas regular folks are going to call shear rate pumping speed. It's the same thing. And shear stress is sort of the same as drag. Okay, so shear rate is the same as pumping speed. Shear stress is the same as drag. Okay, just trying to get you into the club here. Again, there's especially the shear rate versus pumping speed. Now, again, you might not be using a pump, but that's, again, if I want to speak in words that you don't understand, I can say, well, the shear rate of this water is whatever, when actually I'm saying the pumping speed. And I can say the pumping speed is 3 gallons per minute, or I can give you the shear rate in some SI unit that's some arcane unit that might disenfranchise it. So that's why I mentioned that. And okay, then this would be a good way probably to end this before break. This lower graph is one I think you should keep as a mental model. And it's actually in the book, page 115. I know you can't read that, but in your book on page 115, there's a little more elaborate image. But rather than the last image, which shows you a thicker turbulent boundary layer, I think it's more helpful for designers to consider that turbulent boundary layer has a thinner low velocity component to it. So the boundary, the low velocity part of the boundary layer is thinner for turbulent boundary layers. So this is, we're looking at this lower right curve here. Let me get a different color or different highlighter. Okay. So you can see this velocity component here, the low velocity part is very small for the turbulent, and it's higher for the laminar. So this is, oops. All right, so the low velocity part, and you can kind of think of it as this laminar boundary layer is thinner for the turbulent boundary layer, and that's what leads to this. And let me just go a few more minutes. So this is what we looked at before, where you had the roughened section of the bowling ball here, and it caused the separation point to move back to here, whereas this was laminar because of that stickiness of the boundary there, the thickness of the boundary there. And you had this huge area here versus this area here. This is low pressure, low pressure. So you have this produced bigger pressure drag. The laminar on the left has a high pressure drag because you have this big area here of low pressure region. And then we looked at the bowling ball too, or the golf ball in the same vein. So here with laminar, we have this large. Now there's a lot of things with golf balls that maybe, this. You have this big area here versus a small area. So that's related to pressure drag. And let's see. Yeah, this would be, let me just go over these really quick, and we'll take a break. We'll come back, talk a little bit more. I want to talk a little bit about viscosity, and we'll go in the breakout group. So I do have some slides on this. So let me just go over this because I didn't talk about compressible and incompressible. So viscosity is resistance to flow. And I like to think of solids as having infinite viscosity, which is almost true. And like I said, oil is high, water is medium, air is low. It's resistance to flow. And it changes with temperature. Hold my finger up. And non-Newtonian fluids, the viscosity will change with shear rate or pumping speed, which we'll look at maybe today. I hope so, but we'll see. And then compressible and incompressible. Let me go right over to Reynolds, Mach, and Weber. Reynolds number we've talked about. That's basically velocity over viscosity. It's actually inertia over viscosity. Mach number is the speed versus the speed of sound, and or mechanical transmission. So if something is going at the speed of sound, it has Mach 1. Twice the speed of sound is Mach 2. And in a lot of the areas, you talk about units less than 1, subsonic flow. And we'll do a repeat of that as well. So, and then Weber number is velocity over surface tension. Velocity over surface tension. I have a slide on that. Or it's actually inertia over surface tension. That one we don't need very much. All right, we'll look at it a little bit more later. That gives you an idea about atomization potential, whether something, a fluid will break up into droplets. So surface tension is how strong these surface adhesive forces are versus velocity. So as you can imagine, if you want to atomize water, you need high velocity. And Weber number is an indicator, again, of propensity to atomize. So now looking at Mach number, what's interesting with Mach number is when you get near Mach 1, Mach 1, you know about shock waves. And shock waves then act as incompressible fluids. So if we go up to the terms compressible and incompressible, and we're out of time here almost, compressible fluids are fluids in which the density changes if you apply pressure to it. So if I squeeze a balloon, the density changes. Incompressible, if I squeeze a balloon full of water, the density does not change. So compressible fluids are gases, and incompressible fluids are liquids. But there's one exception, and that is high Mach gases. High Mach gases are incompressible, which is why dynamite kills you. So high Mach gases act like a liquid. when a wall of Mach 1 gas hits you, so suddenly you apply pressure to it. It doesn't blissfully flow around you. It acts like a wall of liquid. It has nowhere to go. The density doesn't change, so you get hit by